factor of safety. So here is the stress strain curve for any material. It has a pattern which we've seen, which keeps being stops being linear somewhere at SY yield strength, and then it ultimately fails. We are going to use this thing called SP, which is the proof strength for a bolt. If you're not given the proof strength, just assume, I think it should be 0.85 SY. I think I did a mistake here. Let me just check this. Okay, so if you're not given a value for SP in a problem, it's safe to assume it's 85% of SY. Yield strength is usually given. Okay, so now if FP is the proof load, and AT is the cross-section area of the threads, okay, then it's clear this is basically force. SP is force divided by area, and so I just move things around, compute the force. So this is the proof load. This is the specs for that particular thread. It's not a, it's something which you'll use for calculations a little bit later. Okay, so these are recommendations for pretension. Like this is the force you need to tighten the bolts. You take it to be 0.75 SP or 0.9 FP, okay? And that depends on the connection. So if it's a permanent connection, like a rivet, which we're not going to do here, then it will be 0.9. If it's a non-permanent connection or a reused fastener, use 0.75. So it's by far it's 0.75, not 0.9. We're not going to do permanent connections here. A weld would become permanent, but it's different from fastener. Okay, so now we get to tensile stress in a bolt. This is not a new formula. It's the same formula I wrote earlier, FP divided by AT. But FB is PB plus FI, PB being the load on the member. So if you have a, this is just a recap. Washer, member, FI is always on the bolt. PB is always on the member. So the net load on the bolt is going to be the sum of the two, PB plus FI. And we've seen that PB is C times P. Okay, so now we come to the factor of safety for a bolt. FP.
Yeah, like we were
PB.
Oh, in the equation above, like FP, it says FI is equal to 0.75 times FP.
Yes.
What's that?
FP is the proof strength. Proof strength is here, proof strength. It comes from this point. This is a spec. So when you have the specification. So when you have a bolt, you design it based on some proof strength. And this basically is the diameter of, depends on the diameter of the bolt. So that's a spec. So FP is a spec. So instead of using strength, using force as a spec. And the spec basically is used to compute the preload FI. Okay, so the yield factor of safety is SP divided by sigma B. SP is, as I said, a spec. Sigma B is something which will depend on the loading. So this is determined by the proof strength. So it's more or less a spec. But PB is something which comes from what you're subjecting the specimen to. This would actually be, yeah, this is PB, which is C times P. P is this should be total load, my bad. This should be the total load P. CP is the, PB is the fraction of the load which comes on the bolt, which actually depends on the stiffness times the total load P. So P is here, that's the same P here, times CP, so times C. So NP, factor of safety, is SP divided by sigma B. Sigma B was computed here. You put it there, you get an expression for the yield factor of safety. Now, here's the thing. This NP is usually made very close to 1. Okay, and I think the reasoning is that if you overload these things, you want the bolt to fail first before you fail the members, so you can replace them. So this is like something to remember. Usually we'll make something safe for a plane. Usually factor of safety is like 2 because you want to carry as little load as possible. But for a bridge, it might be 10. But keeping NP close to 1 means, less than 1 becomes, it breaks, right? So it's close to 1. Okay, now we are going to define a few things before we get to a problem. we'll define a load factor. Okay, this load factor scales the load like NL times P. What we'll do is the load factor is defined such that the bearing stress or sigma B equals the proof strength SP or such that NP1. So you remember there was an expression for NP. NP, this is the factor of safety. So all we are doing is saying if NP is 1, what is the corresponding load? So this is the load at which the bolt will fail, right? Because N is 1. If the moment it becomes less than 1, it will fail. But instead of trying to find P, we are scaling P and seeing how much it is respect to P so that we can use it for any design. So here we just, instead of assuming it to be P, we assume LLP because P might be something which is specific to your application. So for a car, P is different from, say, a bike. So P is given, I'm going to find NL such that it just makes it, or just the bolt just fails. So SP equals sigma B, which also implies NP equals 1. We get a formula for NL, which is the load factor. Okay, there's another important consideration when we are trying to understand or design these things. When you have, so this is a consider scenario where there are two members, 1 and 2. You apply load P, P by 2, because it's equally taken by the two sides. We want to figure out if this P increases beyond a certain value, what will happen is these two members will separate. So there will be a separation. Okay, and that is bad because now all the load is taken by the washer. If there's a gap between the two members, that means that they're not transmitting any forces. They're just, the bolt is taking all the stress. So if there's a separation, so how do you find that load for separation? It turns out that we did derive a formula for Fm. So if I go back here, this is the load in the members. It's Pm minus Fi. When this force goes less than 0, we'll have separation. So we go back and put this lecture 29. We put the value Fm equals 0, and solve for that load. So that load P0 at which separation occurs is Fi minus 1 divided by 1 minus C. If you know Fi, you can find that P0. Fi is given by a spec. So that's an important consideration. You don't want the load to be greater than P0. Okay, and finally, we define a factor of safety for joint separation. So this just accounts for to preventing joint separation is just P0 divided by P. We get this value. We just have to check if it's greater than 1. If it's less than 1, you'll have separation. So there are two factors of safety. One is separation. This is, well, the first one was defined here. That's, well, one, this is guarding against yielding. There was another one, load factor. This one just is actually not a factor of safety because it's basically telling you when SP is NB. So, but maybe we'll include it too. Load factor is not a factor of safety. As I said, it's basically something which tells you at what P you will get failure. And then this third one is separation. The members separate. This is the top member, the bottom member, and then washer. So there is separation. Okay, we'll solve this problem, and that would be the last thing. So figure below shows a cross section of cast iron pressure vessel. The maximum diameter of the steel bolt is 6.625. Threaded length is 0.75. Unthreaded is so length threaded is 0.75. LD is 0.75. the area of the threaded portion is 0.226. Okay, so we need to have, so this is just one bolt, we need to use n bolts. So as to resist a separating force of 36 skips. So this force, or resisting force, separating force, I think is it Fi? Okay, we'll think about this. You're given E for cast iron, E for steel. Compute KB, KM, C. Now, the reason why you're given these two is because this bolt is made out of steel, and then this is made out of cast iron, I think. Cast iron pressure vessel, yeah, and the bolt is made of steel. Okay. Okay, so compute KB, KM, and C. C is straightforward. It depends on KB and KM. Let's compute KB. Okay, the formula for KB, this is the bolt stiffness. We did this sometime back. It's basically B, A. So it depends on the threaded and unthreaded part. Let me try to recollect this. This is fastness here. Yeah, here it is. AT ADE divided by this formula. Bolt. Okay, so the values for AT. So AT was given here. AT was given. AD is not given. Okay, AD is actually not, it's very straightforward. AD is pi d squared divided by 4. The d is given as, this is the diameter of the bolt, 0.625. So AT comes out to be 0.3068. Okay, so we know AD, we know AT, LT and LD are known. E is that of steel. Steel is 30 MPSI. So here's the substitutions. 0.326. AD we just computed, it is 0.3068. E is 30 kpsi. AT was 0.326. LT was 75 plus 0.3068. LD was also AT was also 0.75. And then that's about it. So KB is 5.21 ml PF per inch. Okay, next is KM. Okay, now for KM, we need to find the stiffness of these members. Okay, luckily both of them are made out of same material. We actually have to use the cone method. So the cone is, so luckily the thickness is the same. So we know that both of them would have equal stiffness. And actually there was a formula we had derived for this. There's actually a mistake here. This should be LT. Just fix this. I'll post this again. Corrected. Okay, so we need to go back to the stiffness calculations. So the member stiffness, the cone method, okay, so we're going to assume that dW is 1.5 times d, just to simplify the calculation. And then the Km is half using the, so since there are two members of the same stiffness, we can just bypass this and just use this formula. So I'm going to take this formula from 28. and then put it. Okay, in this formula, D is 0.75 and L is, I think, the length of, it's also the thickness, which is 1 point. Here, L is this 1.5, the sum of the two. Okay, what else? E. E is gray cast iron. Cast iron has a E of 14 MPSI. Second. So my bad. This is length 6.625. This should be 0.625. Okay, so Km is 8.95 mlbf inch. Okay, so C is straightforward. It's basically Kb divided by Kb plus Km. So C comes out to be 0.368. So the next question, we need to compute the number of bolts required for a load factor of 2 when the bolts may be reused when the members are taken apart. So let's write the formula for the load factor. So let's see what's given to us. We're given NL, that's 2. We're given AT, that was here 0.226. We are given C, or we computed C. It was 0.368. Okay, so C is done. C is known. AT is known. NL is known. SP, if you see the question, we see that we're given the proof strength is 85 kpsi. So with that, we'll try to compute Fi. We know that Fi for a unused, for a reused fastener is 0.75 FP. This basically came from here, so 0.75 FP. And FP is known to be AT times SP. So this is 0.75 SP times AT. So Fi is going to be 0.75 times SP, which is 85 times AT, which is 0.226. Okay, this comes out to be, Fi comes out to be 14.4 kip. Okay, so this is also known. Now we are left with P. What's P? Well, if you can go to the problem, we see that the total, it says here that the total of n bolts to be used and a force is 36 kip. What this means is that there is a force of 36 kip on the entire structure of n bolts. So the load taken by each bolt is going to be 36 divided by n. So this is the total load. And to compute the individual load P, we need to take the total load and divide it by n. So 36 divided by n. Okay, so we can now use the formula 2 equals SP, which is 85, times AT, which is 0.226, minus FI, 14.4 kip, divided by C, which is 0.368, times P, divided by N. So 36 divided by N. And we can solve for N. Solve for N. And if you solve for N, you get 5.52. Okay, now you cannot have 5.5 volts. So really we need to round it up to 6. So the 6 is the number of bolts needed in order to take this force of 36 kg. Okay, let's solve the last part, which is C. Using the value of n above, determine the realized load factor for overload, the yield factor of safety, and the load factor for member or joint separation. So this is sort of like the design factor and factor of safety. You come up with a number for n, and then when you actually compute the value of n, it comes out to be a fraction. You round it up to the nearest integer, and then you compute uh, the necessary load factor, which will be different from the load factor which was given for you earlier. Okay, so that's what we'll do. So next part C, we'll compute the load factor. That would be same formula as this one. Let's take it, copy and paste. Okay, so we have now NL is unknown, SP is 85, AT is 0.226, FI we computed 14.4, C was 0.368, and now we have to put 36 equally distributed among 6 bolts. So if you use this value of 6, we'll see that NL comes out to be 2.18. So even though the actual load factor desired was 2, because of the design, we ended up with a load factor of 2.18. Okay, the next question is yield factor for safety of safety. So that value is NP is SP divided by sigma B, which we wrote down as SPAT divided by CP plus FI. Everything here is known, so we just substitute 85.226, 0.368 for C. P is now 36 divided by 6, and FI is 14.4. So substituting the values, we get NP equals 1.16. It's important to note that the factor of safety is very close to 1, as what we had told earlier. Finally, we asked to find the load factor guarding from separation. So load factor guarding from separation. Okay, so this is the load factor which will prevent the bolts from separating. So the load factor is given as Fi divided by P times 1 minus C. NO is Fi divided by P times 1 minus C. So Fi is 14.4, P was 36 divided by 6, C was 0.368. Okay, so substituting these values in here, we get NO equals 3.8. So the actual load which it can take is, so P we can go up to 3.8 times 36 divided by 6. So once you hit this force, you will start experiencing, the members will start separating, and so you don't really want to go, you want to be below this load.